Okay, so let's look at an explicit example. And this explicit example just goes back to the rectangular section cross section that we had, and here we're going to say that there's a certain width. Okay, so here I'll put a width A. These are like traditional notations, and width B in the y direction, and then the thing is just extended in the z direction, right? So that's our waveguide. So what we can do in this case is we can solve by separation of variables. Okay, so this field here is a function of x and y by our assumptions. So what we're going to say is that we're going to separate the dependence in x and y in these fields here. Okay, and we can do that either for the B or the E field. It doesn't matter. Okay, so let's just do it for the B field. It's the same equation. So we're going to say that the z component of B in the x and y direction is a product of two functions, one function big X of x and one function big Y of y. Okay, and now what we get when we back substitute into this equation here is that we have a solution. So, you know, I just literally back substitute this B here in the equation for B, and take the usual thing. So these two derivatives act on this one here, but I can also then divide out by x and y. So essentially, let me write down the solution and you'll see how it works. The solution works provided the second derivative of the big X is, you know, some constant that we'll call kx times big X. The second derivative of y, dy squared, is some constant ky squared times y. And at the same time, I want to fulfill the condition that kx squared plus ky squared plus k squared is equal to omega squared over c squared. Okay, you can see that this works out in this equation here, because when I pull out second derivative with respect to x, I pull out the minus kx squared minus ky squared plus this, and then it all is equal to 0. So you see where this is going. We're just going to fit now waves that fit the boundary conditions that we have at these boundaries that we have at x is equal to a, x is equal to 0, or y is equal to 0, y is equal to b. Okay, so maybe in a sense, in view of time, I'll let you have a look at these things, because now it's really just filling in the blanks. But there are a couple of interesting things that occur. So general solution. You see, for the x component here, you need something that that oscillates between these two boundaries. So if I use a general solution, I can write it as a mixture of sines and cosines. So a sine kx x plus b cos kx times x. So that would work as a general solution. The boundary conditions tell us something about all of this. This you have to work it out a little bit. At x is equal to 0 and a, we have that the b in the perpendicular direction, namely in the x direction, has to be 0. Okay, that was our boundary condition. B perp is equal to 0 here, but now applied to the surfaces here and here. Okay, so that's one of the boundary conditions. And now if we have that, then we can look at our other equations here. So the yeah, which one is it? So the bx is equal to 0. Look, the sixth one here, bx is equal to 0. The E field perpendicular is also equal to 0. But then this tells us if both of these are 0, then the dBz dx has to be equal to 0 at this boundary. So that's the kind of result that comes out of this. So dBz dx has to be equal to 0 at these places, and that means that essentially we need to take the big coefficient a to be equal to 0. Okay, so there's this one disappears. It doesn't fit the boundary conditions that we have. Okay, and this also tells us that the kx has to be quantized in units of pi over a, because I need to have the derivative vanishing here and here. So kx has to be an integer multiple of pi over a. Okay, where this one here, let me be clear that it's an m, where this m is equal to 0, 1, etc. Okay, so these are the solutions. Okay, we can do the same thing in the y direction. So so in the end, we get the solution that bz of x and y has the following form. It's got some amplitude, but then there's the cosine of m pi x over a, and in the y direction it's the same thing, but now with an n pi y over a. Okay, where these m and n are just integers. Okay, and this is called the TE for transverse electric MN mode. Okay, so this is a mode where essentially both electric and magnetic field are oscillating in conjunction with each other in strange directions so as to fulfill the boundary conditions, but have this traveling wave in the z direction. One way you can visualize what happens actually inside a waveguide, although I mean I'm not going to be able to show you how to prove that, but if you've got a waveguide, essentially it's as if you had an electromagnetic wave in real space, plane wave, but you've injected it inside and it started reflecting back and forth all over the place. Okay, so, and the point is that you do that to create this kind of standing wave pattern inside the waveguide that is represented by these modes that you have here. Okay, the wave number for such a mode here carries some interesting property, because unlike in free space where omega is equal to ck, there's a more complicated relationship here between k and omega. So in this case here, we have that the k is omega over c squared, and then minus kx squared plus ky squared. Okay, so this is just pi squared with m over a squared plus n over, sorry, that's a b, of course, n over b squared, and then square root. Okay, so so if omega is low enough, k is imaginary. Okay, so given m and n, if my omega is not big enough, then this thing is negative, and the k becomes an imaginary thing, which means that the wave cannot propagate. It's attenuated. As I move along z, instead of having e to the I kz, because k is imaginary, I get e to the minus some number z. Therefore, the wave doesn't propagate. But if omega is big enough, so if you're kind of able to overcome this basic energy threshold in there, then the wave can propagate. Okay, so this basic frequency at which things can start occurring is known as the cutoff frequency. Okay, and this cutoff frequency, it's particular to a given choice of modes m and n, and by definition, it's really just a minimal frequency where these things equal each other. So the you see the omega is just equal to that thing. So this is just a c pi with the square root of m over 8 squared plus n over b squared. Okay, so any wave that tries to have modes m and n needs a minimum frequency in order to be able to propagate. Okay, so then there's lots of discussions of the physics of that thing in there, but that's completely different from what occurs in free space. In free space, you can have any omega. It just sets a very low k if omega is very low. But in a waveguide, somehow you need your frequency of the wave to be faster than a kind of critical reaction frequency of your waveguide. And this kind of critical frequency is this cutoff frequency that you have in there. Okay. Have you seen this kind of physics at all before? Did you know about cutoff frequencies and waveguides and stuff? No? Okay. Okay. So, but you know the importance of waveguides all over the place, right? So it's they're used like everywhere. Everywhere. Right? It's like, yeah. I'm sorry? In a microwave? So a microwave, in a sense, it's not really a waveguide in itself, it's more a resonator. So waveguide is really used for the transmission of things over long distances. So you're all connected in the end to some fiber optic networks, and the fiber optic network, or an optical fiber, is a very good example of a waveguide. Okay, so inside an optical fiber, you can't propagate electromagnetic waves below a certain threshold frequency with a chosen mode that you have in there. Okay, so that's the kind of thing. So you see, it's kind of fun with waveguides, because you can start doing a heck of a lot of complicated things. So here we've used an idealized conductor. Perhaps we can do something simpler at first. Let's fill the waveguide with a dielectric material, and then given a certain permittivity for this thing, and a certain permeability for it as well, then how does the wave equation change? Well, you could work it out. Let's do an even more complicated thing, or just step by step. Let's go back to the empty waveguide, but now let me put a conductor with a finite conductivity as the boundary. How does that affect things? You see, it becomes much more complicated now, because you know that there's going to be slight penetration of the electromagnetic waves inside these imperfect conductors on a length scale about the skin depth, and you should solve the Maxwell equations in the presence of that thing. So what's that going to give? It's going to give a mechanism for dissipation inside your waveguide. Therefore, given a certain conductivity for the material that sets your waveguide, you could compute for me the length scale over which a certain electromagnetic wave like that is damped by a factor 1 over E. Okay, depending on the quality of the conductivity like that. Then you could put those two things together. You could say, I've got an imperfect conductor as the boundary. I've got a dielectric material inside, right? And what's the physics behind all of this? So actually, the physics of a real optical fiber has You want like both these things. If you have a coaxial cable, like the old TV cables, or lots of coaxial cables, presumably still in this building, a coaxial cable is, instead of being a square or rectangular cross section, it's just a circular cross section. You've got an outer boundary, but then an inner wire inside. So now you've got these two boundaries there, and you can also compute electromagnetic waves in these setups here. With imperfect conductors, with dielectrics inside, you can have frequency-dependent permeability, permittivity for all these things, and you can still work absolutely everything out with these assumptions here. Then you can go crazy. You can say, well, let's imagine that I have a kink in my optical fiber. There's a little defect in it. What happens then? Well, you need to solve Maxwell's equations with this kind of new boundary condition there. So you got to change your assumptions about translational invariance, but still, in principle, you have all the mathematical equipment to do all these things. So there are lots and lots of people in the business world and whatnot who have spent their lives computing these things for these very practical situations based on these equations. Okay, the whole basic theory for this all is stuff that you've got at your disposal now. So I'm not going to bother you too much with it, but I think it would be great if, you know, one summer when you're really bored or something, you read up on indeed wave propagation in these setups here. And suddenly what I would hope is that you recognize many of the equations. You say, oh yeah, no, that's just like, you know, the boundary conditions you've got there. Got that from Maxwell's equations. Yeah, sure, a little dielectric here. That's what I need to do here. And then, okay, fine. You follow through, you read what they do. And then they end up doing just more and more complicated versions of what we're doing here for these very simple circumstances. Okay, so that's the kind of point I wanted to make. I mean, it took much more time than I expected, and I'm not sure it was as convincing as I would have liked it to be. I'm not quite sure you'll walk out of here with a great love of waveguides, but I tell you, it's a very rewarding thing to do. I don't know why you're studying physics, but for me, the fun has always been to take real practical things and to understand how I could, with basic theory, compute basic properties of these things. And with waveguides like this, hopefully you've, or you will be confronted with them in various lab circumstances here. And sometimes you can really understand what happens, or you can compute some effect that you really can see. You can compute some dissipation, you can compute some loss rate for these things based on such equations. I think when you do stuff like that, it really justifies all the work you've put in learning the hard theory. You see, waveguides here for me, I like because they start from Maxwell's equations. You only need to know Maxwell's equations. You can rederive the boundary conditions, and then they ask you to solve these things. And these methods that we've learned, like separation of variables, really come in handy if you're able to recognize which symmetries you have and whatnot. You need to solve these linear equations. Little tricks for inverting these sets of coupled linear equations. Use a matrix, multiply by the inverse matrix. All these things are quite fun when you can start doing them more or less, you know, mechanically. Okay, so hopefully this is the kind of stuff that you'll be able to use in other places later on.